To examine how naive Bayes works, we're going to look at this popular small weather data set. This data set has 5 attributes, the final one being the class label, and the first 4 being the individual feature values. These are all categoric values, as you can see here, with x1 taking the value of rainy, overcast, or sunny, x2 taking the values hot and mild and cool, x3 taking the values high and normal, x4 only taking the values true and false. And we're trying to predict whether the person facing these weather conditions is going to play golf, which is a Boolean output, right? A Boolean class of either no or yes. So recall in naive Bayes that we need those prior probabilities as well as those conditional probabilities. We're going to build this up from the statistics on the input features and the output labels. So here, for example, we are looking at the frequency table of a particular attribute, outlook, which is our first column, our x1, and seeing how it relates to this column here, which is our output variable, our output label, play golf. You can see here that when it is sunny, which happens in 5 of the instances, here, 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 and one more here, that 3 of the times in those cases, we actually do play golf. Once here, once here, and once here. So this count is going to be aggregated into this particular quadrant, right? And we're going to do the same for the other 6 parts of this table. Now we have to transform the frequencies into likelihoods by dividing through and normalizing them to a probability. For example, here where we're talking about we actually play golf when it's sunny, you can see that there are 9 instances of actually playing golf. So the sunny types capture 1/3 of them because there are another 4 and 2 cases for a total of 9 total cases. So this is going to be 1/3. We can do the same for the other 6 boxes in our probability table. We also can calculate the marginal probabilities. For example, when the outlook is sunny, how many times does that happen in our data set? What happens 5 out of 14 times because there's 3 cases of which we play golf and another 2 cases where we don't. Similarly, we can do the marginal probabilities for playing golf by itself. Irrespective of the weather, we would say we play golf about 9 out of the 14 cases that is indicated in our data set. And likewise, because this is a binary variable, then 1 minus 9 over 14, or 5/14, is the number of times that we would, the proportion of times that we would play golf without knowing what the weather is outside. Now we're ready to apply naive Bayes. What we'd like to actually calculate is the probability of y given x. That is, the probability that we're actually going to play golf given that it's sunny outside. For example, to do this, we're going to need those 3 probabilities. First, we're going to need the likelihood. That's given right here, right? This is the probability of the data given the label. In other words, in this case, the probability that it's going to be sunny outside, given that we actually did play golf. The second probability that we'll need is the unconditional probability that we actually play golf. And finally, we'll need the unconditional probability that it's sunny outside. I forgot to write this one as well. So here we go. So we can see the same thing here, except we've colorized it a little bit. And we can do the actual calculations, right? So we have 9 divided over here. And since this is a divide through, these two cancel out. And the 5 will come down to the bottom. So we'll get our answer, which is 3/5. We'll actually use all of the likelihood tables to build up all of the information we need for naive Bayes. In fact, these statistics make up the model representation that we are often talking about, which is our H of theta. Now we're ready to apply naive Bayes at test time. And doing that, we have this particular instance that we care about. It's the same as what we just did earlier, except now we have 4 input variables that we care about. For example, the outlook is rainy, the temperature is cool, it's a little humid, and it's pretty windy too. And with that in mind, we want to predict whether we're going to play golf or not. How we do that is pretty simple. We're going to take that particular data instance, X, and decompose it into its component parts, where we're making conditional independence assumptions about each of the input features being independent. So we're going to calculate the probability of playing golf given that data instance, as well as the probability of not playing golf given that data instance. And to do that, we're just going to look up all of the individual features that you can see below on the conditional probability tables. After calculating all the way through, we'll get these values. Just slightly less than 1% for playing golf and slightly more than 2% for not playing golf. Now, these aren't very helpful on their own. What we want is a probability of going to play golf or not. So we're going to normalize these against each other. We're going to add the two of these things together to create a denominator and divide through so that we get a ratio. Because there's only 2 probabilities here, because it's a binary outcome, either yes or no, these 2 are going to sum to 1. But of course, in the case where there's more than 2 outcomes, all of the cases will have to sum to 1. So the answer to our question is definitely we're not going to play golf with 80% probability given what we know of the weather conditions at that time. In summary, we've looked at naive Bayes. Naive Bayes is a Bayesian approach. Bayesian approaches in general handle uncertainty in a principled way, mathematically using probability. Naive Bayes makes a very important assumption. It makes a strong assumption that features are conditionally independent of each other, and often that's not the case. You can think about whether this is okay to violate or not. There are some important problems with naive Bayes as we've represented it right now that are fixable. For example, it doesn't handle zeros of probabilities. So in some cases, and you can find out where in the tables, we have some zeros. When those zeros are multiplied against, you'll end up with a 0 probability. Secondly, it only works for categorical information. So if you have a numeric or continuous value, you have to find some way of discretizing this into bins. We'll handle both of these problems later on in the post lecture.